Okay, so my name is Manuel Uhm. I'm Director of Silicon Marketing at Xilinx, which means that I have responsibility for all silicon at Xilinx. I'm also chair of the board of directors of the Wireless Innovation Forum, which some of you may remember as the SDR Forum. So I've been involved in SDR for a long time. And my partner in crime, Mr. Jason Vidmar, who is our senior system architect for Milcom, Satcom, and machine learning at Xilinx. So today we're going to talk a little bit about AI and software-defined radio. I think most people recognize that these are trends that are converging. And what we find interesting is the evolution of SDR over multiple decades now followed a track that has a lot of parallels that we're seeing with artificial intelligence and processing for artificial intelligence. And specifically where I talk about software meets hardware again, you know, the goal way back in the day of the JTRS program and even pre-JTRS with programs like Speakeasy was to have your waveform run on a CD, yes, a CD, remember those, and just be able to run on a general purpose processor, everything's good, all software. And then of course, reality struck, and it wasn't possible to do that within the size, weight, and power restrictions that you have within a typical tactical radio. And so you needed to tightly couple software with hardware through devices like FPGAs. Well, with AI, we're seeing a pretty similar trend where, ideally, yes, you can just take your TensorFlows and put them into a general purpose processor and you're off to the races. But again, I think we see from a compute density perspective a lot of the same challenges. And so we certainly believe that software tightly coupled with hardware is also going to be the trend for actually applying AI in the field. So going back to SDR and talking a little bit about the history. So SDR essentially is a de facto standard today. It's in every handset in the world. It's in pretty much every radio that you see these days. And we've gone through successive generations. And so it started way back in the day where you had SIGINT systems, electronic warfare systems, public safety systems, all using some type of software-defined radio. And in this case, I'm using the definition that the Wireless Innovation Forum uses, which is a radio in which some or all of the physical layer is programmable. Okay, so by that definition, all these radios were software-defined radio. Then along came JTRS with the tactical radio market, which created kind of this huge disturbance and benefited really from two main semiconductor trends. One was the use of FPGAs for signal processing, and also the availability of affordable RFICs that had the type of dynamic range that was required for our software-defined radios for the military. So from there, technology continued to evolve. Of course, from a processing perspective, there was a lot of benefit from Moore's Law. And so continued to ride that trend. And with 4G, again, you see this situation where every base station and every handset was a software-defined radio. And so that evolution continued. Now we're seeing it with 5G. And the trend now is towards even more integration. So analog and digital integration through products like Xilinx's RFSoC is one example, but there's many other examples where, again, the goal is bringing things together very tightly, have it smaller size, weight, and power, and be more efficient from a processing perspective. Okay, so AI has been kind of a newer domain in terms of the evolution, but as we all know, it's growing and increasing exponentially. And so there's a lot of evolution happening very quickly now. And again, we've seen this trend move from artificial intelligence to machine learning. Now it's all about deep learning, moving from CNNs to DNNs. But from a technology perspective on the semiconductor side, again, definitely seen some benefits from Moore's Law. GPUs have certainly had a large role to play here because, again, throwing tensors at a GPP hasn't practically been the answer for getting AI out into the field and deployed. Certainly FPGAs also have had a place here, and definitely ASICs. You've seen ASICs from companies like Google with TPUs. There's many startups now that have AI-focused semiconductor devices. And so ASICs are coming back into play. There may be a large enough market in the end for artificial intelligence for there to be ASIC-based solutions. So a lot of similar trends that we're seeing here. And of course, what really gets interesting is the fact that these are converging, right? So now you have a situation where software-defined radio compute density was scaling beyond what GPPs could do, and AI with the same problem, and now you're combining them, which makes for an even worse problem, as you know. And so really, we're having this convergence from an SDR and AI payload, and it started with cognitive radio. And when I say cognitive radio, I'm referring to the way that Joe Mottola originally coined the term, which was a radio that actually had some form of cognition that could actually identify scenarios like, okay, the warfighter is getting bombed, send a distress signal, right? Or call in a strike. Not the sort of lesser term, which has kind of become more commonplace, which is a frequency agile radio. So really a radio with some form of cognition. It could also have adaptive characteristics on the waveform, where again, it's adapting dynamically. It's not doing it because a human is changing some type of setting. It could also be doing interference mitigation. So cognitive radio is pretty well established from a technology and a payload perspective. So why not cognitive radar, right? So having radars that have pulse frequencies that are repetitive and different dynamics, dynamically, different times, different waveforms, being able to be more stealth, right? So cognitive radar is also something that's starting to become more commonplace. So now you have this plethora of data, right, that you've generated through all these cognitive radios, through all these cognitive radars. Well, you need to turn that data into information, right, into intelligence. And so how about cognitive SIGINT, right? I mean, the human ability to process that amount of data is extremely limited. And so the demand there is now for cognitive SIGINT systems. And these SIGINT systems are doing things like detection and classification of unknown signals. Is just one fairly simple example. Well, now you have all this information. What do you do with the information? Right? So you have to turn that information into action. And so now you need cognitive EW systems. Right? And these EW systems may be doing jamming. They may be doing anti-jamming in the RF domain. There's many different things which they could do. But again, the goal is to have a system which has some level of cognition, some level of AI implementation and capability. And I think overall, the goal is really to have what, in the defense space, I think folks would call a multi-mission, situationally aware payload. Okay, so a payload that's capable of doing radar, radio, signals intelligence, electronic warfare, be aware of the situation and act accordingly. And to do this, you're going to need SDR and AI technology. Okay, that's great. So let's come back to the processor problem. Right, so I talked a little bit earlier about Moore's law. Most people are familiar with Moore's law. There's plenty of other laws in the semiconductor world. If you combine Dennard scaling with Moore's law, basically what you get is a doubling in performance per watt every 2 years. Now, it's generally agreed upon in the semiconductor industry that we reached the end of this probably about a decade ago. There are other laws that have kicked in, like Amdahl's law, so having multi-core, going multi-threading. But the issue there is Amdahl's law states that performance doesn't scale linearly, right? And so you can't just throw more cores at the problem. Eventually you saturate, and you just run out of juice. So we've made pretty incredible gains, and customers, consumers have expected this. And unfortunately, we're at this point now with processor and semiconductor technology where that's just not good enough. You can't just rely on Moore's law to solve the problem, especially a problem as tough as software compute performance and AI compute performance together. So moving forward in the industry, there's been talk about domain-specific architectures, because by no means does the semiconductor industry throw in the towel. Of course, there's new things. So what are these new things? What are these domain-specific architectures, and how do they impact how one would design the processor for a software-defined radio and an AI intelligent radio? So if you look at the landscape today, again, general-purpose processors are not going anywhere. They span a plethora of applications. They're applicable in a wide variety of scenarios, if not almost all scenarios. But they're limited on the performance and performance per watt. ASICs and ASSPs, this is interesting because there was a lot of talk, actually, over successive generations of semiconductor technology that, okay, it's too expensive to do ASICs and ASSPs. And for the most part, I'd say that's been true. We've seen design starts slow down significantly. But actually, recently, they've actually started up again, despite the cost of doing ASICs and ASSPs. And part of that is, again, this evolution to trying to achieve artificial intelligence type processors, which require something different. So for markets with enough volume, it's a big bet, but ASICs and ASSPs certainly, I don't expect to go away anytime soon. And if you look at your handset, that's going to be the typical solution that we're going to see. Now, FPGAs kind of fill that gap right in the middle there, where you need something that's more compute dense, has more performance than a general purpose processor, but has more flexibility, more ability to differentiate and evolve than an ASIC or an ASSP. It's a trade-off because it's never going to be as power efficient or as low cost as an ASIC or ASSP when you talk about per unit price. So if that's where we are today, domain-specific architectures we see as fitting somewhere around here, where you have something that Xilinx has called an ACAP, Adaptive Compute Acceleration Platform, and I'll go into the details of that in a minute. But it's a domain-specific architecture, which means we've specifically done things in the silicon targeted towards specific domains, which means it's in some ways less general purpose than a general FPGA. Okay, so then why does it seem to be more applicable? Because the way we've implemented it through heterogeneous processing actually means you can scale it to multiple different domains. And as folks know, SDR and AI technology are broadly applicable to many markets. And it allows that increase in performance and performance per power that customers are used to getting, even though Moore's law has basically come to an end. Okay, so I'm going to talk quickly through the Adaptive Compute Acceleration Platform. There's one here. So these devices are real. And I'll just quickly go through it by going through the name. So why did we call it an ACAP? Well, adaptive, I think that speaks for itself. Multiple workloads, it's kind of what Xilinx is known for with previous generations of FPGAs. So again, with an ACAP, we're still benefiting from that adaptive nature. Compute acceleration, okay, heterogeneous processing. It's clear one processor type isn't going to win. You can't just use FPGA fabric. You can't just use a GPU. And you can't just use a GPP, all for a variety of different reasons. And so the goal here for us has been to combine the best of all those different processor types to address as wide a set of markets as possible, including SDR and artificial intelligence. So we have ARM-based scalar engines, general purpose processors. We have our fabric, our logic, which are what we call adaptable engines now, and intelligent engines, which are vector-based VLIW processors and the DSP blocks from previous generations of FPGAs. But I'll spend the most time talking about platform because actually this is what really distinguishes an ACAP, because everything else here is also applicable to FPGAs. So what's the difference? What makes an ACAP an ACAP? It's really in the platform. And the first thing I'll point out is having this software programmable silicon infrastructure. Okay, so many of you may realize that we have something called a network on chip in this device, something we've not ever had before. And when I started in this role at Xilinx, I kind of said, okay, that's cute. We have a network on chip. Well, so does every ASIC and ASSP in the world. Well, when I dug more into it, I started to realize, okay, what we've done is actually very unique and very novel. Because if you look at ASSPs and ASICs, they have a very defined data flow with very defined bit widths, data rates, throughputs. Well, FPGAs in previous generations and ACAPs have to have flexibility. They have to be able to change bit widths. They have to be able to support different latencies. They have to be able to be deterministic. And so you can't just have a preset network on a chip. You actually have to have a programmable network on a chip. And so that's what we've done, where you can change and specify bit widths. Those can change as the algorithm changes or as you have different algorithms. You can specify constraints around latency. You can have quality of results. and specify basically algorithms that would be deterministic. So this is definitely something unique. It's hardened infrastructure, and yet it's programmable. And that's part of how we get the reduction in power consumption, the increase in performance per watt. And then from a software perspective, because it's not enough to have a good processor, right? You have to be able to program it. You need development tools, and really for the first time, this is a platform that we've targeted where a software developer could actually develop without having to touch RTL, without any VHDL or Verilog knowledge at all. And that's, again, very different than before. Part of the other thing that we're focusing on with ACAP is to do what we call accelerating the whole application. So it's not just good enough to have these AI engines. Okay, we have these AI engines. What are those? Well, Jason's going to talk more about them. But they're essentially doing things like linear algebra, matrix math, things that are commonly used in AI inferencing algorithms, as well as things like beamforming and other types of 5G processing. But in order to make that work, you have to have memory hierarchies. You have to have I/O so you don't have any bottlenecks in the system. And so we've put in place all that hierarchy, all this network on chip, all this connectivity, all this I/O to ensure that from a system level, you can bring in all the data, do all the processing you need, and then make decisions. And in this case, targeting things like a tactical edge system where you might have to do adaptive beamforming, where you might have to do anti-jamming, tactical networking, etc. Okay, so really quickly, I talked about software before. Really the goal here is to be able to have a different set of tools that appeal to different types of developers and not force developers to all have to know VHDL or Verilog. Vivado is always there for those who do understand VHDL and Verilog, but for those embedded developers that are used to doing things like using SDSOC and programming in C, using Vivado HLS, for example, there's an internal codename tool called Scout that will actually be announced in October at Xilinx Developer Forum. And that allows folks to use C and other OSs, drivers that they're used to. And then at the framework level, we have another tool which will allow folks to basically take tools like TensorFlow or PyTorch and actually implement those algorithms on their platform. And so if we come back to our multi-mission situationally aware UAV payload, we're looking at this type of scenario where our goal is to, again, provide as much of the platform, as much of the solution, real-time operating systems, but also support AI through tools that AI developers are familiar with and allow our customers to focus on the applications, the comms, radar, SIGINT, and EW. And very quickly, before I hand over to Jason, I did quickly want to flash up this slide. The two series that we've announced with Versal so far, AI Core and Prime. Obviously, AI Core is the one that we're focusing more on today because it has the AI engines in them. But you will notice going forward, in fact, in November, we will launch AI Edge, which will be of interest to a number of folks in the room because that's going to be where we're focusing on performance per watt. AI Core is really around compute in the data center. Edge will be AI at the edge. And then AI RF, for those of you familiar with RF SOC, there will actually be a next generation of that, of course, and that will be found with the Versal AI RF series. And with that, I will hand off to Jason.
Perfect. Thanks, Manuel. Pleasure to be back working with Manuel again at Xilinx. And pleasure to be here at the GNU Radio Conference. Thank you to the conference organizers. Thank you to all the attendees. Just great to have a chance to speak with you today. I've been a long-time lurker of the conference. Glad to finally be here. So as Manuel mentioned, I'm a system architect at Xilinx on our aerospace and defense team. And I wanted to key off of Manuel's introduction and talk a little bit about I wanted to talk about really just trying to quantify, to an extent, some of the problems that we're facing on the front of advanced software-defined radio. And I realize that that term itself is a bit ambiguous. I'll try to help define that. I really want to focus more on advanced software-defined radio requirements. I'm going to go ahead and build some of this out, just in the interest of time. Really from a wireless physical access layer perspective. How do we handle that problem so that we can enable a whole bunch of interesting SDR applications that run on top of platforms? And if you look at a couple of trend lines in a few very prominent categories here, there's multiple ways to break this down, but it's interesting to focus on, hey, what's going on in terms of requirements and demand for more capacity from our software-defined radio systems, for more autonomy from our SDR systems, and then also for more resiliency from our SDR systems. And capacity, I think 5G is kind of the poster child example to look to when it comes to quantifying, hey, what's the difference between 4G capabilities and 5G? And ETRI was put out this graphic. They published this a few years ago at a 5G working group, and it just really compared metrics and a number of different parameters related to overall SDR performance. And a few things that jump out are peak data rates for 5G, 20x increase over 4G to 20 gigabits per second. A total area traffic capacity increase of 2 orders of magnitude, 100x. Latency improvement, 10x, down to 1 millisecond latency in these systems. What type of hardware platforms are required to realize this? From an autonomy perspective, you could kind of fit in the word cognitive radio up there. That's kind of the end goal from an SDR system. And I think we've come to realize, out of this community in particular, there's been a lot of great work published on how deep learning is not only revolutionizing fields such as image classification, but what about RF classification? And I think if we looked at, this is not inference specific, but it gives us a hint as to the growth in compute complexity for neural networks and deep learning neural networks. This is a comparison put out by OpenAI, comparing AlexNet in 2012 from a total computational workload perspective to AlphaGo 0, put out just in 2018. It's a total increase in petaflop days of 300,000x. It's 5 order of magnitude increase in 6 years. Moore's law alone would be about 8x increase at that same time. So we know that's not going to get us there. And then I think a more difficult element to quantify precisely would be the resiliency side of things. Certainly from a defense perspective, our critical communication systems are having to operate in a highly contested environment, a highly contested spectrum, not just congested, but contested. So the adversarial capabilities that are out there just with standard off-the-shelf hardware are very prominent. So how can we, from a signal processing perspective, enable more resiliency in our critical communication systems, and what sort of compute cost does that have? Those are the sorts of things that we're interested in solving. I'm going to do some build-outs here. So the dramatic effect is a little bit lessened, but I want to be conscious of the time. So enabling technologies, there's more than just a few, but I certainly would point to the prominence and the rise of direct RF or high IF sampling data converters. That's giving us access to millimeter wave spectrum. A wide range of companies able to field and produce this technology. Going along with that, array antennas, phased array antennas, and then taking a look at just some of the advances that we've had for deep learning and the compute optimizations associated with that. The thing about millimeter wave is it's great that we're able to access millimeter wave now frequencies. Certainly we get some benefit of increased bandwidth, but we still have to observe physics. The physics say that with shorter wavelengths, for the same amount of power, we have less range, right? So effects of the environment become more prominent at millimeter wave. Foliage penetration, building penetration, multipath effects are prominent. So the range that we have has to be considered, and this is leading to a lot of innovation in the antenna side of things. We're seeing prominent implementation of phased array systems at the base stations, but it's good for more than just commercial comms. It's also good for interference mitigation against bad actors, anti-jam systems. So that picture in the lower right-hand corner, that's kind of some images of nulling representations on a controlled reception pattern array antenna. And I'll talk a little bit about the compute cost for that. But lower left-hand corner, if we're trying to get a sense of compute, everyone kind of wants to classify their cats and dogs. That's 2-3 years ago sort of results. But out of this community in particular, there's been some interesting advances for RF classification, particularly modulation classification. What's the compute cost for that, and how do we build that into a system that is more spectrally aware? So I thought I'd draw some comparisons here, do a quick time check, between space-time adaptive processing techniques that are needed for applications like adaptive beamforming and nulling and deep learning applications. Are they similar? Are they different? And what can we kind of take away from that? So This is actually a picture, I'll admit, this is from 12 years ago, this picture, made by Xilinx. We've been doing adaptive beamforming for a long time. What's different now is you're starting to see this capability fielded into comm systems on a wide scale. So the whole notion here is that if you have not just a single antenna element, but an array of antenna elements, you can exploit the spatial diversity in a manner that you can detect the direction of arrival between a signal of interest. And as long as your jammer is not in the same location as the signal you want to identify, you can use that to discriminate and ultimately increase gain along a path of interest and cancel out gain along an interference path. And the process for doing this involves, if it's a linear problem, which depending on the antenna technology, there's some considerations here, but involves a lot of deep linear algebra compute. The process for solving for an optimal set of weights that might maximize the gain of a signal of interest is kind of summarized below here in this Wiener equation. But essentially what you're doing is you're taking a covariance, you're estimating the covariance matrix for that antenna array. That's a vector cross product. And then you're needing to invert that matrix and multiply it times a steering vector. So the whole process of doing that matrix inversion is very compute intensive. You know, dust off your favorite numerical methods textbook. There's many, many different solutions to this class of problem, and well studied through the years. Often in FPGAs, we're looking at matrix decompositions, QR decompositions, Cholesky decompositions, as we factor this matrix. Generally, it's a complex value problem. It wants to have higher precision if the array size is large. You know, single precision floating point, for instance, and we're looking at anywhere from thousands of floating point operations to megaflops per decomposition. So an actual real-time system might be looking at gigaflops to perform this optimal weight vector estimation. Kind of comparing and contrasting this, well, what about deep learning, and particularly deep learning with convolutional neural networks? Well, also at the heart of this problem, kind of the bounding compute problem, ends up being that convolution operation. This is naturally something that has cubic compute complexity, but there's a number of factors involved that can lessen that. But ultimately, you have a 2D matrix multiply happening here. So if you look at a network like ResNet 50, that is a network that has a compute cost of 7.6 billion operations. So depending on how fast you can compute, that controls your latency through that network. So these are different problems in terms of precision, but they're similar in overall compute density. So, at Xilinx, if we're considering or we're looking at being able to design a hardware platform that's capable of addressing these two vastly different areas of SDR, I think that previous exercise is very instructive because, first of all, it lets us know that we really need to be able to support a wide range of precision. And in the AI engine that's present in the ACAP architecture, we do have a mixed precision, a wide range of precision selection available. So everything from real data types, from floating point precision to real on the left-hand side, to complex, native support for complex data types, very important for RF signal processing. And this is applicable not just to RF, but a wide range of digital signal processing applications. So really, how do we design an architecture that can accelerate these sorts of linear algebraic operations? And then kind of taking it now more toward the processor itself. So again, speaking to kind of the design motivations for the AI engine processor that's implemented in ACAP, we'll actually construct kind of a multi-processor unit here. So we definitely want to have some sort of scalar processing capability coupled here. There's more than just vector operations that we need to do with these sorts of SDR-related tasks, but we definitely need a vector unit, both floating point and fixed point. We need a memory interface, and we'd like to be able to stream data at low latency into and out of this. So with the design of this class of processor, we obviously get parallelism we can exploit in the data itself. Look at your favorite textbook for an FIR filter, get rid of the for loop, replace it with vector multiply, or 2D convolution, replace it with a matrix multiply. There's data parallelism that we can exploit with the vectorization of a processor such as this, but also we get instruction parallelism. This is a very large instruction word processor. We can do multiple operations in parallel simultaneously, and the left-hand side shows the individual operations that can be done in one clock cycle. A couple more slides to wrap this up. So the concept here is this isn't done on an island. We'll actually create this vector-aware AI engine processor, and we'll couple this together with a non-blocking high-speed interconnect. This is an AXI interconnect switch fabric, and that's also further coupled then to direct attached memory. both local and neighbor memory direct attached. That further is combined into an array whose size will vary based on the size and the capability of the device, right? This could vary anywhere from tens of these to hundreds of these in the largest device. And then we ultimately want to be able to couple this sort of vector processing array with other heterogeneous capabilities on a platform. So for instance, if we're doing RF processing, can we get those high-speed RF samples in from either ARF chip or an on-chip direct RF data converter into the programmable logic fabric, and then ultimately efficiently into the AI engine array. So, I mean, aside from signal processing, we could also think about, well, how do we utilize this capability for machine learning inference? How can it be optimized in similar fashion? In this case, we like to think about the AI engines as being a vehicle for an overlay to be provided on top of the AI engine array that optimizes that array for a specific precision type and a specific workload type. And in this case, we actually will use the programmable logic fabric as a very tensor-aware, low latency cache system. So we don't have to go to external DRAM to fetch weights and activations at a very rapid pace. We have enough depth in on-chip SRAM where we can store those in a very deep on-chip low latency buffer and have that optimized and feed data into the AI engine. AI engines also optimize for the sort of cascade streaming operation that is often seen when you share weights between the same input. Finally, wrapping up here in a couple of slides, what we have looked at is just a wide range of signal processing problems and machine learning problems and how vectorizable they are. And as you might suspect, they are highly vectorizable. These are some of the efficiency calculations we have for various operations such as machine learning convolutions, FFTs, and digital predistortion algorithm being implemented on the AI engine. So you can see very high utilization. The whole idea is we always want to be doing compute if we can while we're fetching data. We don't want to have any stalls, and that's what the efficiency applies here. So it's a very novel architecture in terms of it's a low latency streaming vector processor. So hopefully that gives you a sense of some of the motivations. As Manuel mentioned opening, we definitely see a convergence in more and more compute being driven out to the edge of our systems and needing to be fielded in a power efficient manner in our radio architectures. And in that sense, we're really seeing a convergence between demands for artificial intelligence and machine learning and what we've historically seen for SDR. The SDR world's driving for more capacity, autonomy, and resiliency. We know that Moore's law is out of steam. Even if it was at full steam, the 2x gain every 2 years isn't enough. We really need architectural innovation, and adaptive compute acceleration platforms are our response to this new reality. So again, the picture is a little bit of a blown-up picture of what Manuel has in his pocket. I'm not sure if what he has in the pocket is electrostatically alive still, but feel free to stop by and take a peek. Thank you for your time.